In this video, I'm going to implement a MATLAB function to represent the Lotka-Volterra predator-prey model. Okay, this is a simple application of multivariate model, as we've seen in the previous video. So first, let me have a look at the system of recurrences that describe this model, and it's given right here. So we have two populations: R, the rabbits or preys, and F, the foxes or the predators. Okay, and we are given initial conditions here, and then we have a system of recurrences that describe the evolution of these two populations. This term here represents the reproduction of rabbits, while this term here represents the death of the fox population. Okay, if they don't eat the rabbits. All right. But here we have the predation term, which couples the two variables R and F, okay? And you see that it depends linearly on both R and F, okay? And this is typical to the Lotka-Volterra model. We have four parameters in this model: lambda, mu, A, and B, okay? So let's try to implement now the system of recurrences in MATLAB. All right. So let me first create a function in the right folder. Okay, and here I don't want any input. I'm gonna call this function, for example, Lotka-Volterra, and I don't need any output as well, because I'm going to write a set of commands here directly inside the function. Okay, including the plotting command. So what does this function do? Okay, always give a quick description as a command. Okay, so here this function will, so it computes the evolution of predator and prey populations as described by the Lotka-Volterra model. Okay, this is a standard model. So first we always set the parameters, okay, and give them values. So here we have four parameters. The first one was lambda, okay, which is a reproduction rate for the rabbit. And let's this to, for example, 0.005. Okay, this is just an example. You can then play around with the parameters as you like to see what's the effect on the evolution of these two populations. Then we have mu, which is a death rate of the fox population, and let's take it to be the same as the reproduction rate for the rabbits. Okay. Now we have the parameter A, okay, which is involved in the predation term, and it's actually the rates of rabbits caught per fox. Okay, so let's take this number to be small. In general, it's quite small because each fox won't catch that many rabbits. For example, say 5 times 10 to the negative 6. And then we have a parameter B, okay, which represents the number of foxes born per rabbit caught. Okay, and let's take that number to be 1, for example. Okay, although we'll see later what happens when we take it a bit smaller. Now we define the number of time steps. Okay, so which represents the maximum value of n here, the index that we're going to compute. Okay, so let me call it capital N, and let's take, for example, 5,000. Okay. Now I'm going to initialize my two arrays R and F, okay, which will contain the values of the sequence defined, by these recurrences. Okay, so R will contain the value of the sequence Rn, okay, and F will contain the values of the sequence Fn. All right. So I initialize R, so the rabbit population, and we initialize using the zeros command as usual. Okay, so it's an array 1, n, okay, which contains zeros, and how many zeros? Well, exactly capital N. Okay, so here it's a 1 by n array. Okay, so it's basically a list of n zeros, and n here is 5,000. All right, and we do the same thing for f. Right, then we want to initialize the first value in the array, okay, and the initial conditions are given here, so that's not a problem. So r of 1, we take it to be 4,000, and f of 1, take it to be 2,000. Okay, and then we can start implementing the system of recurrences, okay, using the for loop. So I start my for loop using 4 as usual, okay, and I take small n to be my index, which varies from 2 to capital N. Okay, and then I simply implement these two recurrences in parallel, okay, and you see that each recurrence, or n, depends on the other, fn, but that's okay because they will depend on the other recurrence at the previous time step. So we can implement the two recurrences at the same time step, okay? So let me write r of n. The nth entry in the array r is given in terms of the previous one, so r of n minus 1, that was plus lambda times r n minus 1, okay, the reproduction of the rabbits, minus a times r of n minus 1 times f of n minus 1. Okay, that's the predation term. And I do the same thing for the foxes, f of n, which is f of n minus 1 minus mu times f n minus 1 and plus b times a times r of n minus 1 times f of n minus 1. Yep, I forgot to close this bracket here. There you go. Semicolon. Okay, so see, I have implemented these two recurrences here, which are exactly those represented here. All right. Good. So these will work fine, okay? And you may think, well, hold on, how can we calculate r of n here in terms of f while we haven't calculated f yet? Well, actually, it will be fine because we use the value of f at the previous time step, which has been calculated, okay? So for example, in the first step of the loop here, well, while n will be equal to 2, then we will calculate r of 2, and that will be given in terms of r of 2 minus 1, which is r of 1, r of 1, r of 1, and f of 1, which are both given here outside as in the initialization step, okay? And then the same thing for f of 2, okay, will be given in terms of f of 1, f of 1, r of 1, and f of, okay, that's good, I got that, f of n of 1, which is 1, okay? So that will be fine, okay. Now I will want to plot these two recurrences, okay, so let's do a plot. So I define an array containing the first capital N integers, the first 5,000 in this case integers. So let's, for example, call it x vals for x values, okay, and that will be 1 colon n. I can now write the plot command, okay, so plot, where I'm going to plot both arrays R and F here on the same figure, alright? So remember, it's always first the array containing the x coordinate, which is what I've defined as x vals, okay, and I'm going to plot the evolution of the rabbit population against these, okay, for example in blue, and xvols, okay, to plot also the population of foxes, okay, and for example I can do that in red, okay, and that should be all. So let me save that here. Let's go back to the command window and call Lotka Volterra. Okay, and you see I get this curve here, which is quite typical to the Lotka Volterra model. We have this periodic behavior, okay, where the two populations will interact and change over time. All right, so as the population of rabbits increases, okay, while the number of foxes is quite low, so they are not eaten much, okay, well, the population of foxes will increase because there's a lot of rabbits, so they can finally reproduce, okay, and as the number of foxes becomes quite high, okay, then the number of rabbits will start to go down, all right, and as the number of rabbits is low enough, then the foxes will start to starve, and therefore the population will decrease as well, and we have this periodic behavior. All right, so we can try to see what happens when we change the parameters. So for example, if I change this parameter to 0.5, okay, that represents the number of foxes born per rabbit caught, okay, so I have that, all right, which is probably a bit more reasonable, okay, but still this behavior, this periodic behavior is maintained, it persists, okay, and it's typical to this Lotka Volterra model. All right, so you can play around with the parameters even more, okay, to get different kind of periodic behavior.